Let me make sure that's running. This might not stream to the right page, so just, yeah, it is not going to do that. Actually, maybe it will. We will see. I'll let you guys know if it works. All right, this should be the correct one. I will double check. All right, I believe we should be good now.
Okay, so I'm gonna go ahead and get started then. So good afternoon, everybody, and welcome to HackMIT 2020, the panel judging event. So we finalized the top 8 teams of our competition, and they'll be presenting their projects in front of our judges today. So why don't we go ahead and have our judges introduce themselves?
Sure, I'm John Cohn. I'm at the MIT IBM Watson AI Lab. I'm a huge MIT nerd, co-founder of Vomit, Vermont's own MIT club, course 6, 1981, and very happy to be here at HackMIT.
Hi there, I'm Matthew Russo. I'm a machine learning engineer at Cambridge Mobile Telematics, graduate from Cornell University in 2018, and we're one of the sponsors for this competition.
Hi, I'm Raj Singh, product manager at InterSystems, down the street next to Sloan School at MIT. I am a course 11 urban studies and planning graduate from earlier this century.
All right, thank you to all our judges. So why don't we go ahead and head over to our teams who will have 5 minutes to present their projects and then 3 minutes to answer any judge questions. So is Loci, and you can go ahead and start your presentation.
All right, thank you so much, Michael. We talk a lot about Zoom fatigue, but never the problem of Zoom scarcity. A video call is lonely. It is created, it is configured, and then it's destroyed. Its entire life is just as a link. And this made sense for one-off meetings, but not for much else. And in 2020, video calls transitioned from a niche to a necessity. They need to work for everyone. Zoom scarcity especially challenges organizations who are trying to translate complex systems into individual unstructured video calls. As university students, we know countless of our peers who spend hours every day keeping track of the 20, 30, 40 different links just for their classes and clubs. And dealing with this unstructured, disparate data is hard because the human mind doesn't think linearly. Our minds are networked and associative, and we intuitively understand that which we represent spatially. So why don't we organize remote work spatially? It's been done before. HackMIT built a playground, a Club Penguin-esque world for hackers to walk around and talk to other hackers and organizers and sponsors. Stanford built Club Cardinal, a browser game that serves a similar purpose. And Gather.town tries to bring some of the spontaneity of a house party to icebreakers and to club meetups. But these are singular solutions built to solve singular problems. And they're almost exclusively used at a small scale as proofs of concept or as a gimmick, rather than as a fundamental feature of the organization itself. The problem is that remote work lacks place. So we set out to build this sense of place at scale. We developed the tools for any university or any company or any conference to build its own playground, its own Club Cardinal, its own Gather.town. We integrate seamless video conferencing so people can join and leave rooms whenever. We use machine learning computer vision to auto-generate these spatial streetscapes and we leverage cutting-edge urban design to optimize these places for collaboration. We built Loci after the method of Loci, the memory palace. Now, there are two main interfaces in Loci characterized by the two main use cases. The first is a user. And now we're going to examine this as a typical freshman student in computer science at the University of Illinois. They often take a class called CS 196 as a supplementary addition to the required initial class. Now, for this student, Loci is a centralized place where they go to do their work. Entering a building opens its corresponding video call. But because a video call is tied to a building itself instead of just a link, it is persistent. Computer science lectures, for example, are always held in the computer science auditorium, while your discussions may be at the corner of, say, Broadway and Prospect. And if you want to meet one-on-one with a partner, you pick out a small house, and that's a meeting room. They are digital streetscapes that are organized like real campuses. The second use case of Loci is the organizer. Now, for them, Loci is a system of tools for their organization to build and configure these streetscapes that the users will live and work on. They can start with just a drawing, either something they've actually drawn out on pen and paper themselves, or a floor plan that they want to start from and base it off of. And then we use OpenCV computer vision to turn that drawing into a starter city. And then from there, they can manually add new buildings, they can drag them around, they can place them, and they can edit and configure them as they see fit. They can change the capacity, they can change the building style. They are really building a city for the members of their organization.
All right, so next we're going to talk about some of the challenges we faced. So one of the big things that I found when going through this project was I was afraid we're going to run into problems with assets. Because we have so many buildings, we had a challenge like that. So we created City as a way to demonstrate how our system can handle load. So this city has over 50 buildings, yet because we're using Flame Engine for Flutter, we can simultaneously run these, each of which has their own separate video call room. So this means that no matter if you have a small group of friends or you're a large corporation, our app can handle your needs.
Another cityscape that we focused on was the snowy city, just to focus on how customizable the modular tiles and modular buildings are in our system. And I'm an urban planning student, so I was excited to bring in some of the things I've learned, which is including having different diverse group of functional buildings, having open spaces so people can interact and have organic communication, and also just having personalized elements, such as in here we have Christmas trees and a reindeer, just to make it so the people want to come back and interact with the space and it's not just a one-off event.
And
And I think Sterling's mic is cut out. Sterling just messaged us and said his computer is frozen. Sterling developed the computer vision model. He can talk into the specifics of it, but we use OpenCV to turn an image into a pre-processed, an image such as this into a pre-processed cityscape. Thank you, and we're now open for questions.
I guess I can start. So I was curious first, have you looked into any competition in the space? I know, for instance, the company I'm at, we used a company called Sakoko for a moment in time. Definitely some differences between your product and theirs. But I was just wondering, one, if you looked into that, and two, have you thought about the problem for businesses, at least, of engagement? You get a lot of people who are kind of stuck in doing calls and Zooms the way that they're used to. Yeah. And then sometimes getting them to log into something like this can be a bit of a hurdle. Just what are your thoughts on that?
Well, so I'll talk a little bit, especially on that hurdling. One big burden for the current setup is that it requires a large number of logins. So every time I join a Zoom link, I need to provide an individual password. This became a thing after Zoom bombing was very common. Each Zoom meeting was locked with individual passwords. And from a security analysis perspective, we really want to look at the weakest link. And these passwords are very easy to share, very easy to link because they're distributed to a wide number of people. And so both in terms of fatigue of people wanting to do things the same way and in terms of security, if we do it with a consolidated system, then we also consolidate the logins. And so one benefit that we can pose to old-time users who are used to doing things the way they are is if we can reduce the amount of overhead per meeting, because we have them pre-configured, because they're persistent, then we can reduce your number of logins, which one, reduces your workload, and two, makes it more secure because we can use more secure forms of login for these consolidated logins, just exclusively using OAuth rather than just simple password protection. As far as the competition, I have not heard of the particular company you were talking about. I forget the name of it, so I don't think I can comment too much on it.
I had a couple of questions, two different questions. One was the last part that you just described quickly. So the OpenCV link is that you would draw a layout and it would digitize. Is that? Go ahead.
Yeah. So unfortunately, Sterling's not here, but my understanding of the way he explained it to me is we use a contour detection. So we base, if we look at that actual contour map, we base the location based on the position. So we just project that onto an isometric grid. And then we base the capacity based off of the size of that a particular rectangle or square that you drew. And so this could be something that you just hand sketched just as a rough estimate to get you started and just place buildings onto a map. Also a cool application we think is there's a lot of existing office floor plans. And if we could scan those and just use those as starter boilerplates, just replacing rooms with buildings and hallways with streets to give it a little bit more spatial understanding, then what we do is we provide a more intuitive experience for the users while also maintaining a simple to get started system.
Was that, I got what you said. Was that used to generate any of the cityscapes that you did, or was that just something you explored?
So we, none of the particular examples that we have was generated directly from a particular drawing because we use that as a starter. So usually we drew like 5 buildings. Teddy, if you want to show right now, like if we have a building, actually, I don't know if Teddy's on right now, but if we have like a drawing with 3 particular squares, then we would scan that and it would start with 3 houses laid out in that particular area or buildings scaled up to the size of the square. And then we built it up around that to add more density. So the green map, the quad map, actually is a map that starts out as an auto-generated one.
Oh, okay.
Yeah, I guess the best way to explain that is it's a layer thing. So the base, like the grass and the trees are there, and then the buildings are auto-generated on top of that. And then we have a few different base layers that we can alternate between, and then buildings placed accordingly on top of them. And streets.
Thank you to Loci for that presentation. Let's go head over to Latent Space for their 5-minute presentation.
Wait 1 second, let me share my screen. Okay, here we go. So is everyone ready? Hello, everybody. We are Latent Space. As we all know, real-time collaboration during the COVID-19 pandemic is extremely hard. And it's even worse for music production. Let's take a look at the latency values of some of the most prominent video calling platforms. Zoom's latency is 135 milliseconds. Google Meet's is 100 milliseconds. Jitsi's is 500 milliseconds. And the thing is, even though these may sound pretty small, humans are naturally able to discern any latencies that are above 10 milliseconds, which means that these platforms' latencies are extremely large. And the thing is, with music production, synchronization is vital for music recording and production. Current audio codecs, as you can see from these latency values, aren't optimized for remote music production. That's why minimizing latency is needed for collaborative music creation. And that's where Latent Space comes in. We provide zero latency and smooth calling. Latent Space is a novel approach to communication. With the power of autoencoders, which are a special type of neural networks, we optimize audio data transmission by domain. So in other words, the genre of the music that's being transferred. The audio payloads, so the actual audio files that are being transferred from one caller to another, are reduced in size by 78% than those that are normally transferred by Zoom or Google Meets, which drastically decreases the latency. This enables musicians and others to synchronize their music as closely as possible, which is extremely important.
Our main technical advantage is our smart audio compression. We use recurrent neural autoencoders to compress audio into unstructured genre-based data. Also, our use of peer-to-peer web RTC technology further decreases this latency. Finally, all our calls are decentralized, which means the data never leaves the browser. Here's a demo of Latent Space.
As you can see, we're pretty in sync and this is using Latent Space platform.
I'm so sorry for our terrible, just like musicianal skills, but I think the technology is pretty promising.
And now this is with Zoom. As you can see, because of the latency, we're consistently 1 beat behind message, and that continues throughout the entire recording. So you can see the difference between our algorithm and Zoom's natural.
This is from my perspective. Okay, so how it works is that we have a Heroku front end with HTML, CSS, and JavaScript, and we use TPUs with TensorFlow for distributed training on GCP for several hours on an array of 64 TPUs. So how autoencoders work for us was that, for example, you have an input, which is, for example, the blue on the left, which is actually just a really long numpy array, which is the representation of the WAV file, right? A chunk of the WAV file, actually. And it is then brought down to the red in the center and sent over the network. The same exact autoencoder ML algorithm then takes that and then blows it up into the final output that is trained to be as similar as possible to the input. And the idea is that theoretically this would allow so that a lot of the noise would be able to, in the original long array, it's just going to be which is not really necessary for reconstruction. It can be reconstructed or can be brought down to a small size, and also that it provides for like very specific, with the training data all being related to just music is really powerful in terms of very good compression for specifically this one domain. So we think that music is only really the first part of this technology. I think with data of other domains and more training time, we could also take this into other industries, such as business conferencing, real-time live gaming, something like that, and even further, possibly into AR, virtual learning and collaboration. And as we can see that what coronavirus has shown us that this trend, for example, Twitter has moved completely and said you can just leave and just work remotely. There will just be this trend that continues where more and more the physical distance between you and I are less and less relevant to how we communicate and how we collaborate. Thank you.
So here's just a quick appendix from for more of our technical advantages, just if any of you are interested. Yeah, we're now open for any questions you may have.
What did you mean by genre-based compression? I mean, when you do the autoencoder and you look at the latent space, is it like how do you apply a genre, or what did it pick out in terms of genre?
Okay, so what we really mean is that although Zoom is like a really good with their algorithm, it's not AI obviously, but like just their traditional human-crafted algorithms for compression of audio before they send it over. It's really good at general audio compression. We're really talking about kind of like audio that's related to just music, and we're just trying to get at the idea that it's really good at this one particular domain and perhaps not generalizable to other domains such as talking, but possibly in the future.
Yeah. And building off of that, the reason why this the genre and the domain in this compression is extremely important is because when we have these more narrow domains that we're looking at, the data can be compressed even further, but still maintain the accuracy of reconstruction afterwards. So with a really compressed internal, like as you see the red block in here, the smaller it is, the less time it'll take to be transferred over the network, and then it'll still be accurately reconstructed.
Just curious, what was the training data set that you used for training? Because you did, I guess, was it specific music files? Was it was it you guys speaking into the mic, like a computer microphone? Like, did you generate the audio files that way, or sorry, not speaking, but playing music into a computer microphone? Because I'm guessing that would be sort of the source of the data that you would normally encounter. And then also, do you have any kind of benchmark or comparison for your compression as opposed to just traditional compression methods?
Right. So we were taking this data set with it was something like 14,000 different video files, or sorry, like WAV of different classical as well as relatively modern non-copyrighted music, and we just found it was like 14 gigabytes, and we just ran it on that. Afterwards, if you're interested, I can show you a link.
And on your question about the baselines, right now our main baseline that we've talked about is, as you said, the traditional sort of solutions like Zoom, and that's what we focused on improving. In terms of other autoencoders that are able to compress this audio data, it actually is a very new field. One of the things that we started out with on this hackathon was actually looking at a lot of the research papers on using VAEs and autoencoders in general for basically audio modification. And a lot of these papers have only come out late 2019 onwards. So it's a pretty early field, especially in the application to audio, but we're definitely, like you said, that's definitely great feedback. We'll definitely try to find some more baselines and improve our algorithm.
Okay, so thank you to Latent Space for presenting. Let's go over to our next team, Space Tunes.
Yeah, just a sec. Okay. Can you see the screen? Just waiting for my teammate.
Yeah, I can see it.
Okay. So, hello, my name is Elena Ruiz, and I'm here with Jaime Cantu, and we're both from Monterrey, Mexico. We're Team Sparrow, and we are here to present Space Tunes, which is an app about learning music in a fun and simple way. And thank you. We hope you enjoy.
Okay, so Space Tunes is an application that helps people learn and visualize music in a more accessible way. The idea was inspired by Duolingo and the way it perfectly combines education with gamification. A lot of people are interested in learning about music. However, the confusing and technical jargon discourages them from continuing their education. With this app, we've made an abstraction of music theory and presented it in a way that requires no previous knowledge, and it's visually engaging, and most of all, it's fun. During this pandemic, learning new hobbies can really be a lifeline. Aside from providing entertainment and distractions, it's a wonderful motivator to learn and develop new skills. So now I'm going to hand it over to my teammate Elena to talk about the more technical aspect of development.
Yeah, so we developed this in Unity because we thought it would have many options to make like the app accessible, because it has built for a desktop application. We can do it on, like, host it as a WebGL, and we can also do mobile applications. And the way Unity works, it's powered by C# scripts. They work under object-oriented programming. And half of our team had little Unity experience before this. So all of the assets, like music, sprites, scripts, obviously, we did together in one day. And so now we are gonna demo so you can see our work.
Sure, I'm gonna go ahead and share my screen. So this is the application running on my computer. This is our start screen. So we're gonna go ahead and click start, and we're taken to a level selector. So going off on the first level, we have this empty constellation, and our objective is to place these stars that each one represents a note in the correct order or the correct position. And when we get it right, we get a little indicator, and then the song plays by itself. So now taking it to like a more advanced level.
Jaime, I think we're not hearing any sound. If you want to retry sharing the screen.
With the sound. Sure, give me a second. Okay, I think it should be working now. So here is the level again. I'm just gonna go ahead and place the notes. And as you can see, the song plays out in the specific order. And here on the bottom, you get more information about the technical concept that you're learning about. So now taking it to a more advanced level, you have to complete this shape.
Yeah, and what we plan to do in the future is make like more lessons like this with their own individual levels, so that the user learns about music theory kind of without realizing it, kind of like cognitive learning. So like by the time they're done with the lesson, they already know how to distinguish new notes and terms that would have been really confusing just like reading normally and stuff.
So in this level, we reference our team name, Team Sparrow. So we have a little bird constellation, and as the user places the notes, they are going to realize the shape that it's forming. And this is a much more visually engaging matter of reading music rather than reading it from typical musical notation. So I think that would be it for the demo. So I don't know if you have any other additional comments you'd like to make before we go to the Q&A.
No, we can just jump straight into the Q&A.
Perfect.
Yep.
What was the overall tech? What was it implemented in?
We used Unity, and Unity uses a C# language.
So
it's a game engine. Mm-hmm.
You said that. Oh, yeah.
Yeah.
And then I'm just curious. So you mentioned I guess this is mainly geared towards sort of teaching music theory. And then have you thought about any ways to tie this to different instruments? So for instance, imagine that, I'm trying to learn how to play the piano or the guitar. And I need both, I need both the technical skill of how do I actually play the instrument and then combine that with the theory. Any ideas on connecting those two?
Sure. Actually, the technical knowledge that the user will gain from this application is the groundwork for any instrument. So that is useful. And also we had planned to make a creative mode where the user can freely place around the notes wherever they'd like and connect them and make their own songs that way. and give them the ability to export them as audio files. So in that way, it could be its own instrument by itself.
Thank you.
Yeah, the idea is that this app is going to be kind of like a more beginner friendly point for people who are interested in learning music, because I don't know, we feel like as soon as you have an understanding of music theory, you can take on any instrument, or at least make it easier for yourself.
Gotcha. Yeah, no, that's a great idea. Thank you.
Thank you.
How is the theory or the tunes encoded? Are they in a separable piece, or are they hard coded?
We use objects, right? So each star has the possibility of becoming a different tune, and we just kind of assign it. So in a creative mode, you would be able to manipulate that as well.
Yeah, so we basically have a function that like creates the object, and as a parameter, we pass along the note that we want to play.
Are there any more questions? If not, I think we're done.
Okay, so thank you to Space Students for that presentation. Our next team is Eyesight.
Okay, can you all see this fine?
Yep.
Okay, awesome. So hello, everybody. First of all, I just want to say thank you all for tuning in today and for giving us the chance to be a part of the top 8 teams. Today we'd like to share our HackMIT project, which is called Eyesight, and it is a real-time AI-powered narration app for visually impaired people. So the problem is that there are millions of people across the globe who suffer from some type of visual impairment. You know, obviously this is a massive spectrum where on one end, there are some people who are fully blind and cannot see at all. And on the other side of the spectrum, there are people who have only a mild impairment and, for example, cannot see long distances and can only see the distance of their phone. Nonetheless, it is a pretty widespread issue where people with visual impairments have to rely on some kind of caretaker who is constantly by their side and is narrating what environment they're in and what their surroundings are. This works, this is like a proven model, but obviously it reduces the individual's sense of independence because they have to rely on somebody else to navigate through their own world. So our idea was, what if there was a way to do this completely through the camera of your phone? So you would have human-like audio describing these real-world scenes that the camera is seeing, and this would not only help people experience the world and build community amongst other people with similar impairments, but it would also help them to navigate the world on their own. And this is the general premise of our project, generating real-time captions of a user's camera feed and converting them into human-like text-to-speech narratives with anyone's mobile phone. And I think it's important to note that, it's important to note that especially in today's scene, where social distancing and being aware of what is in close proximity to you is incredibly important, we saw a really big need for this app, and we decided to just dive right in and try to tackle it. So essentially, with the power of an image captioning model combined with geographical and weather data, all combined into GPT-3's model and read out to the user using a realistic text-to-speech model called WaveNet, we were able to build our app. And so we used Flask, HTML, CSS, and Python for our backend and front end respectively. We used PyTorch for all the machine learning models. And the models that we used, as I mentioned, was GPT-3 and WaveNet. GPT-3 was used, we'll describe a little bit more later on how that was used. And then WaveNet was the realistic text-to-speech model. And then we also implemented some of our own image captioning and activity recognition models as shown on the slide. And then we also implemented our app using several APIs, the first of which is Google Cloud Vision, which helps us do object detection and localization. The second of which is Denscap, which helped us do image captioning. And then the last two were weather and geolocation, which obviously tell us the weather and location of whoever's app they're at. And now Jaydev and Anirudh will talk a little bit more about the techniques.
Cool. So I can talk about the workflow that we'd envisioned for that. So we wanted to make it make it able to take data from multimodal source of data, not just like what you're viewing from the camera through image capturing, but also speech. And the hope behind this was GPT-3 would be able to understand the location and time, along with the sounds that were being classified, combined with the captions which generated from individual frames being passed into an image captioning model, and convert this into a very human-like audio description. And you may have seen audio descriptions of Netflix movies if you look at different languages, but something like this isn't really out there for somebody who has a visual impairment and wants to experience, let's say, a park or a train station in a much more detailed way, unless there's a human standing next to him who is whispering these things into his ear. Yeah, this is a workflow. We pass these inputs in the GPT-3, use Wavenet to generate text-to-speech in much more human-like manner, and save these sentences in a queue, and eventually read this audio out on the front end. Next slide. So we did do a few iterations. I implemented Facebook AI's state-of-the-art flow-fast video recognition model, but because none of us had an NVIDIA GPU and there was large latency, we realized that we were better off just using an image captioning API and building out a proof of concept that works pretty well. We also removed sound classification and added weather and location API calls, so that there was more context added as to where the person is based on his or her actual physical location. Okay, next slide. Anirudh, do you want to take over?
Hi guys. So the purpose of our app is to also provide a community for people. Imagine a person is in a park and they see a beautiful scenery, and they can just capture that audio description on their phone and then mark that audio description on a map, and then other people send that to other people, or they can just directly see the map. This also promotes a community for people. They can just click on it and see the audio description of a particular place. So yeah.
This is a sample GPT-3 conversion, and the response you see at the bottom is completely unchanged. The top is a schema that we use as input to pass into the GPT-3 API. As you can see, if you were a blind or a visually impaired person, you would prefer something a lot more human-like, like response at the bottom versus the one at the top. Next slide. Natasha, you want to take over? Natasha? Okay, her mic isn't working. I can do the next two slides. Some of the challenges we faced was getting the phone camera feed to stream into our backend and be able to parse these frames and pass these into our models. I'm also running some of the state-of-the-art models without GPUs on our machines. And the next slide. A few additional features we have is plan for the future is make voice-based querying so that one can query past experiences as we would if you had Google Photos on your phone, and also store history of audio records and share these with the rest of the community who is also using the app. Okay, I think that concludes our presentation, and we'd love to take questions.
So I just had a couple. So I'll ask a similar question to what I asked Latent Space, which is, I mean, obviously I saw you used WaveNet, and then I think Facebook's, is it SVR? I forget the exact name for it. So, I mean, kind of there, I assume there's not really a baseline out there to kind of do sort of, because you're basically doing image/video captioning while also adding in some other data sources to kind of augment it is kind of the gist of what I'm getting. Is that a fair representation?
That's a fair representation. And I think the real value add is GPT-3 is only 2 months old. We haven't seen anything like this in the text generation space. So the hope is not only will GPT-3 put these sentences together in a lot more human-like way, but also use previous context it's seen during its training to make these more detailed and more human-like.
Gotcha. And did you have, I mean, I guess, how well were you able to evaluate the success of this? You showed one example. Were there, was that like, just coming from a machine learning background, it's like, I'm always a big skeptic. So it's great to see kind of more successful examples on like a very wide set of things. Did you have success in other ways? You don't have to prove it to me. Just
yeah. So that's a good question. I will say this particular example was one of the very good outputs we got. The other training examples we had in our GPT-3 prompts involved train stations and beaches and whatnot. We also had one example of like just a living room, which worked decently well, but I wasn't as descriptive as the example we showed.
Okay, that's fine. No, thank you.
I was going to ask the same question as Matthew in terms of, with GPT-3, which is absolutely amazing. I mean, what I would worry is that it would fill in with facts that weren't actually there. Did you find that some of the annotations actually embellished upon the scene in ways that weren't factual?
We did, and we were thinking of ways to combat against that, but we didn't really have time to do.
Do you have any thoughts of how you would do that? I mean, because that's hard.
Well, so one of the most common issues, or one of the most common problems that came up when there was a bad response, was stuff that simply wasn't there. And that's easy to check if none of those objects were detected in the object by like a object detection model, which we run. So a sanity check on that aspect is easy. But for like the color of someone's shirt being misdetected or some additional details being filled, that's a harder problem. But it's a lot less. It's a lot less of a important problem, I would say.
Very cool. Thank you.
Okay, if there are no more questions, let's go over to our next team, the virtual classroom.
Hey guys, so we're just going to quickly share our screen.
Yeah.
Oh, it's here, sorry. We should start video. And desktop one. This is the whole thing, right?
Mm-hmm.
Sure. So can you guys see our screen?
Yep. Yes. All right. So hi again. We're the virtual classroom. We're high school students from Canada. My teammate Arad over here will be presenting the problem we were trying to tackle.
So obviously with this whole COVID-19 pandemic going on, I'm sure a lot of you have seen that schools aren't able to open back the way they normally would. Kids are, every school has to have an online component because we have to manage space issues in the school and stuff like that. And obviously we're 4 high school students attending school that has an online component. So we can see a lot of these issues that affect a lot of us. Student engagement, learning environment, student participation in the online classroom is nothing like it was in the real classroom. We can see like even us, it's not the same, but for younger kids, it's a whole different level of issue, right? Because they need the student engagement, they need the learning environment, they need the participation so much more than us. They need to stay engaged in what they're learning in order to actually retain the information. And it's so essential for the young students' emotional growth that they have these social interactions in school and they actually like talk to their friends, which is really not happening in these online Zoom and Google Meet sessions. So we wanted to go out and find a solution for this issue. And here's what we came up with.
So in order to increase the amount of engagement and the amount of interaction that students are having with each other and the teacher, we decided to create a VR classroom that simulates as realistic of a classroom environment as possible. It allows students to view lessons from the teachers in real time from the safety of their own home.
They're able to also interact with each other. So each student can see the other students sitting at their own desk. They can see them turning their head with the VR set we have, and it's extremely cheap. Like every student probably in Canada already has an internet connection. They have a smartphone, right? The only last thing they need is this Google Cardboard, which is just a cheap piece of cardboard with 2 lenses, and it acts as a VR headset. And all it does is it makes that image from the phone look like a real classroom environment. Costs like what, $5? It's extremely cheap and affordable.
Okay, so we've got some images from our student view, basically what the student is seeing. So in the bottom left, you'll see our overall classroom view and all of the desks and the blackboard at the front. And at the top right, you'll see what the student sees through the Google Cardboard, but obviously it'd be one image and it'd be 3D. And at the bottom right, you'd see basically we've got an image, which is a teacher presenting live onto the blackboard. And in the cardboard, it would look like the teacher's presenting live, but they can turn around and see other students, etc. So next we've got the teacher view. So basically we've noticed a problem with all of our classes where teachers are having a hard time, dealing with Zoom and Google Meets. There's too much stuff. They're not sure what to do. So we wanted to make a really simplistic UI for them. And this is basically stage 1 of our UI. And yeah, so for every student in the classroom, it shows where they're sitting. It would show their name. And for students that are not sitting anywhere, there'd be like empty desks. And basically the teacher would be able to, mute certain students based off of this. They'd be able to drag students around and change their seating, etc.
And one other important component about this teacher app is we wanted to make it as simple and in one product as possible. So what we did was as soon as you open this link in your web app, what it does is it starts streaming your video and audio stream. It sends it directly to an API we used called Agora, and that sends it to the cloud. And then students in their Unity view in the Blackboards can see right here, as you can see over here, there's this teacher presenting. That's all done through the teacher app. Once this teacher opens up their app, their webcam and the microphone stream are live sent straight to Agora, straight back down to the Unity apps. And the students can see it all in real time along with their fellow students. So we wanted to show you a quick demo just to show you how we made it. So we used Unity for the majority of it. So you can see here, there are the individual desks. Here are some sample students we have. This is the Blackboard that you would see. And I actually have a working version of it running on my phone. Obviously, you probably can't see it as clearly right now because it's camera on a camera, but this is what it looks like. You have the fellow students sitting around, you have the desk tables, and you have the lesson playing at the front. And if you were to run it, you would be able to see, sorry, okay, you know what? We won't worry about that because the Zoom is blocking it off. But if you were to run it, you'd be able to see, we have a sample video running right now in the Blackboard, and the teacher would, that's basically to simulate what the teacher would look like when they're presenting and how the students would see it with their fellow classmates and the actual teacher presenting.
Yeah, so finally, we wanted to look at the future. So my teammate Kareen here will talk about it first. Yeah, so this was like an MVP, a minimum viable product. So there were a lot of other features that we were hoping to implement perhaps in the future. One of these is like a whisper feature. So students can talk to each other, like the person sitting directly adjacent to themselves. We also wanted to introduce a lot of other common functionalities of RTC. So like breakout rooms, whiteboards, like Zoom has all of that. And also like other teacher controls, like as Madhu mentioned before, the muting and the dragging around. We also
one major thing we wanted to import was a reward system for the students. So obviously students at a young age, something they're like really, they really like phone apps, right? And something that would be really cool is if they could actually like change their avatar and skins and stuff like that so that they could stay more engaged in the classroom and stuff like that. So that's something we also wanted to implement in the future, just like a reward system.
Yeah, we think that would be really important because the teacher would be able to award points to the student based on good behavior. And yeah, so that brings us to the end of our presentation.
Yep, so we already did that. We basically use all these platforms, Google Cardboard, Agora, Unity, Firebase, C#, Swift, and HTML5 to build all of this. And yeah, that's how we built it, and that's what it does. So do you guys have any questions?
And you started from scratch.
Yeah.
We did start from scratch.
Nice.
What we actually, we didn't, to be honest, we didn't completely start from scratch. What we imported was just a couple of chairs and tables, but we built a classroom then. And the student models, Matthew here, he built them completely from scratch in Blender. They can do all the raising hand animations. They can sit down, they can stand up. They do all those animations.
Yeah, and me and Kareen spent our time, working on the teacher side of things and the streaming video and receiving video
with Agora.
Agora. So that took a while, but we got it done somehow.
Yeah.
Yeah.
The VR component was a library that we imported from Google. It's called Google Cardboard XR, I think.
Yeah.
That basically got all the head movements and stuff.
Yeah.
So we didn't have to do any programming for that section.
And sorry, just if I missed it. So the stream that shows up in the like the Google Cardboard VR experience from the student looking at the teacher is essentially just a simple video stream that the teacher provides.
Exactly, yeah, it would be a basic video stream of the teacher's webcam or their computer screen. For now, we just put a sample video in the Unity for like demonstration purposes, because Agora is like, you have to start it up and it's really hard to present in a virtual presentation. But essentially it would work if we were actually testing it, yeah.
And in the future, we'd want to implement something like, you know, a whiteboard feature where they can basically on the blackboard, the teacher would be able to draw, and then it would show up on the blackboard as they were drawing, basically. You know, kind of similar to what Zoom has, but it would be cooler because it would actually be like a classroom. And also we'd have like, you know, screen sharing capabilities. We'd also want to make like interactive objects basically in the classroom where they can like, you know, interact with like books on shelves and open them and read them, or the teacher can assign tasks and they can get separated basically. Yeah.
So just trying to make it as close to a real classroom as possible.
Pretty much.
Awesome. Thank you.
Sure. Yeah. Thank you.
Thank you. Nice. Nicely done.
All right, thank you to the virtual classroom. Let's go to our next team, Virtual Learning Toolbox.
Okay, hey everyone, we're Megan Fasella, Nicholas Karan, Tommy He, and Alexander Karan, and our project is Virtual Learning Toolbox. So the goal of our project is to minimize the remote downfalls of the online learning experience. And we want to do this by giving teachers tools to lessen the atmosphere of a remote environment by implementing the more immersive and even expected aspects of a real life one.
So one feature that we implemented was the virtual gesture controlled whiteboard. So basically, the user can wave their hand in the air during a live stream, and this will basically track their hand to sketch diagrams.
So as you can see in this video, the green box essentially denotes the location of the hand, and then we have the blue line that follows the top left corner of the green box, and so that draws it. And then we have extra key bindings that denote like starting and stopping to draw. So then in this instance, we're just like drawing a graph, and this can be like easily extended by like adding more key bindings, maybe for like different colors and options. And then at the end of everything, you can clear off your like virtual whiteboard with the press of a key as well. And then for the implementation of this, we used an open source neural net that was coded in TensorFlow. And then we used OpenCV in order to draw on the actual live feed. And then one of the issues that we first encountered is that the boxes sometimes would be very like jittery. They would kind of like jump around a lot. So we had to like filter it to allow only input from one hand at a time. And then, yeah, we added toggle keys for turning the drawing mode on and off.
Yeah, so another feature that we added into our program was basically audio polling and summarization. So the teacher can ask a question to the class, and then students can verbally respond. And then our program basically takes those responses and analyzes them concurrently.
So here we're going to see a quick demonstration. So at the beginning of this video, I'm going to be giving an example response to a professor's question.
To produce reliable and accessible code for the general population.
And so then
to produce reliable.
Using a speech-to-text API called speech recognition, we convert that into text, and then and then I show here, we have some other students' examples. So because ideally this will be used on an entire classroom of students, I've written up some extra examples, and we pass that into our main function for this tool. And then as you can see, we have two main outputs, which serve as two different assessments of the documents. So the first one assesses them based on what the algorithm believes to be the most important words. So the teacher can get kind of a quick glance through and see what the student's main points were. And the second one computes that embeddings that will basically compute the similarity between the pairwise similarity between all of the documents. So the teacher can use this in order to form breakout groups between students that are either similar or possibly even dissimilar. So I mentioned the speech recognition API. We also, and then for the first form of analysis, we use TF-IDF, so term frequency, inverse document frequency, term weighting in order to determine the most prominent word in each document. And then we also used glove embeddings to produce the similarity embeddings for the second metric.
Okay, and one more feature that we have in our program is hand raising recognition. So if a student has a question or just has to raise their hand, the system will recognize this and let the teacher know. And similarly, when they put down their hand.
So as you can see in the demo, the student is lifting their hand and then it's tracking the position of the hand. And when the student has their hand up for enough time, it recognizes that the hand is raised. So then this could be used to send a notification to a teacher. And it's more like a real life experience with raising your hand and the teacher gets notified of it. So we started off by trying to train our own neural network to detect when a hand is raised or like predict when it's raised. But after a lot of trial and error, we decided to move to using the actual coordinates from tracking the position of hand from the hand detection system from before. So we predicted whether it's raised or not based on clustering a set of points in the previous 30 frames or set amount of frames, and then seeing if the hand stayed in relatively the same location for a set amount of time.
So possible extensions include integrating our tools into a video chat platform like Zoom. Also, obviously training the CNN model for image classification. And then also implementing different hand gestures to control the drawing, like starting or stopping drawing.
Are you ready for questions?
Yeah.
What pre-trained model did you use? Was it PoseNet? Or?
Are you talking about tracking the hand?
Tracking hand and drawing. I'm just curious what model you used. You said
for training the hand, it was like an open source public model, and it was trained with a MobileNet, and the drawing was just with OpenCV right on top of the.
Oh, that, yeah, okay. Nice.
I guess maybe more of a comment, but I think the hand tracking for the drawing was pretty cool. Did you guys, because I noticed it was a little like, obviously it's a little noisy based on the hand motion. Did you guys think or try at all to smooth sort of the signal? So, literally you could do like, if you're expecting lines, you could do linear regression on sort of like the points that you capture. Just that was a comment, I guess, just something that I thought would also make them a little cleaner, a little crisper, but it was very, very cool way you did that.
Yeah, it's definitely something that we want to do if we had like a bit more time. Like after the project ended, we tried to like basically just take it like every 2 or 3 frames rather than actually graph every frame, and that already like improved it by a lot. So we could definitely like do like a regression or something.
We had ideas for like, different kinds of shapes so that the user could select what kind of shape they want to draw or what kind of diagram, and then like determine the size based on like their hand gestures.
Nice.
Yeah, good ideas.
Okay, so if those are all the questions, let's go over to our next team, Navscape.
Yeah, so can everyone see my screen?
Yeah.
Yeah. Right. Yeah. Hi, hey everyone. I'm really excited to be here as a part of my team to present a product called Navscape. So now let me jump right into it. What is Navscape? So, why is it not? Yeah. So Navscape is basically an indoor navigation system that we have come up with. Now, in reality, like when suppose you go out and you want to go to a new place or you want to go biking to a random area, you just whip up your mobile, go to Google Maps and search, okay, I want to go here, it'll give you a path and you just follow that. It's as easy as that. But when it comes to indoor navigation, especially in a large building that you have no awareness of, it is really difficult to navigate from one room to the other. Now, inside, obviously, GPS can't be used. So as a replacement for that, what we have used computer vision. And for finding out a path from one point to the other, we have used RL. and we have combined it all with Unity. We'll give all demonstrations for that. So we started to do this project basically because we felt that once the lockdown in all countries start easing up and things start slowly getting back to normal, in the post-COVID world, it will be very difficult for people to analyze that, okay, I want to go to this place or not. Like, is there too much crowd? Should I be going there or not? So these all things can be easily like solved with our method, because it also gives a live track of the people in the room, which you'll see slowly as I come to the demonstrations. So yeah, I'll explain the approach as the demonstrations come up. We have a proper demonstration. I'm just showing you the Unity simulation and CV mapping so that I can show you the basic UI. We wanted to make an app, but unfortunately, because of heavy bugs in Android Studio for some reason, I couldn't get the app working. But yeah, this was our idea basically, that there would be a small map window where it will show where you are exactly in the room and where do you want to go to. It will track that. You can put in an input for a room that, okay, I want to go to this room, and you press go. It will track a path for you, to chart out a path for you. And yeah, if you want to like do something else, you can also hit a simulation. So I guess this is like, you'll be able to understand this better as we get to the demonstrations. So Uni, could you please
yeah, I'll share my screen. Yeah. Can you guys see my screen?
Yeah.
Yeah. So here's the computer vision part.
Yeah, so basically the computer vision part has two aspects. One is the human detection aspect, and second is just mapping them out on a 2D plot. Now, the detection one is actually relatively easy because it's a very old problem of human detection. Networks like YOLO and many of them are existing. But thing was, we tried to use the heavier models, but it was giving a lot of latency. So we switched to a mobile SSD mobile net, which is, it doesn't have that much of latency, but yeah, it's not that accurate. But this is just a proof of concept for now. So what it does is that it perceives the depth of the person based on the area and the I won't get too much in depth right now, but it perceives the depth of the person and the position exactly on this thing and translate that in using a function that we made onto a 2D map. So yeah, that's the two aspects, detection and mapping. So you can move on to the next part.
Yeah, I'll move on to the next part. So the next part was a reinforcement learning algorithm. So here it is. So what's happening here is we took this image from Google. This was the blueprint of a regular apartment somewhere in the world. So we use this apartment so for navigating the person. So let's say that you are in room number A over here and you want to go to room number G. Now there are many paths that are possible, and one might even arguably say, why not just use some traditional method like Dijkstra's algorithm or A-star algorithm to find the shortest path, and it will take him there. So the disadvantage of this method is that, let's say, like my friend Atta said previously, in a post-COVID world, let's say there are a lot of people already present in room number C. So each of these rooms are having a CCTV camera using which we are using the doing the human proximity estimation, which was shown earlier. So let's say it has been detected that room C has a lot of people available. So you might want to avoid going to this room to get the disease. So instead you will want to take an alternate path, and this property of choosing the right path given this current scenario is being handled by reinforcement learning. And this reinforcement learning is generally used to make self-learning robots or video game agents that play games on their own. But we tried to implement it here as to bring novelty to a concept. So so ACHG is the traditional path that one would take to go from A to G. But if, let's say, I block this room C because it is overcrowded or some natural disaster occurred or some fire broke out or something, so it will reroute the agent to go from A, E, J, I, H, and G, because even though it's a little longer, it's still safer. So
Only we have less time, so can we just move to simulation for now? We'll explain this later.
Yeah. So that's the RL working on IBM Watson. Then I'll show you the simulation part. Yeah. Devyani.
Yeah, all right. So now we saw the CV working, which basically tells us what is a crowd situation in a particular area or a room. And then we saw how the RL was using that and, letting the people know which areas or which room we should be dodging. So right now the Unity, the path sequence which we get from the RL algorithm, which is the safest path for a person, we feed that to this Unity like a 3D simulation, and this shows how the person moves from their current path to the nearest exit, as this particular simulation is showing, demonstrating right now. And this is based on the map which my friend Unikrishnan earlier showed. So this is a predefined map on which the Unity simulation has been done. So yeah, we are done. Any questions?
Our idea was to maybe do an AR agent or something of sorts, but yeah, so this was our basic concept. We had a lot to unpack here, so sorry, I think we went a bit over. But if you have any questions, please.
Yeah, I guess I can ask the first one. So you kind of skipped over it, but I actually do want you to go in depth. So how were you handling kind of based on the position of the camera, being able to infer the depth
right.
of people and then kind of computing distance?
Yeah, right. So the initial idea, only can you go to the CV simulation?
Yeah, I'll open that, yeah.
So the basic idea was we tried two approaches. The first approach was that you take the size, when you detect the person, the bounding box that is being formed around the detected person, it has a certain area, a certain height, certain width. So as you go further from the camera, the field of view, the area that the box covers decreases because the person in the field of view grows smaller in size in the field of view. So we took that into consideration and we tried to chart out with for example, this path is, let's say, 20 meters something, for example, and we know that average height of a person is, let's say, 5'6". So using that, we found out a few things and tried to find out the depth with that perspective, but that had a lot of bugs. So we found another code online, open source, which seemed to work well for depth. Again, this is the output that the code is giving. But yeah, that was what we did for depth. So that is your y-axis. Your x-axis was basically the positioning in the frame, left to right. So that's how we kind of plotted on the map.
Gotcha. Cool.
Did you give any thought? I know this is just a demo, but did you give any thought to privacy? I mean, the thought of putting cameras in rooms, wouldn't fly.
Yeah, right. So we don't expect the for example, some mall or some plaza wants to implement this idea. So we don't expect them to set up some new AI cameras or like some companies have their own smart cameras. We don't expect them to set up that. What we want to do is that just have a CCTV recording, like the ones that are already existing CCTVs. We just take that footage because you saw this quality was really low. It was not that high quality an image that we need really heavy models. And we have a server dedicated for that plaza, that area which we are working on, and that code runs on that server. So we don't really need those AI cameras that can actually have a risk of maybe your face is being detected or something like that. No, we're not doing any of that. So we hope that privacy will be covered at this point.
Yeah, and that's kind of the selling point of our idea, that this thing only requires CCTV camera footage and our little algorithm, because so that means that this is a easily scalable idea, because normally the indoor navigation systems use many more sensors which are just sophisticated. So this is more of a simplistic approach to solve the problem.
Like as Uni said, a lot of people, a lot of indoor navigation systems do exist to date, but all of them use heavy sensors, and for every doorway, for every pathway, they have sensors which tells them, okay, a person has crossed this checkpoint, time stamp, and they have a lot of complicated processes which are not bad, they're really accurate, no doubt. But yeah, that also increases the cost, and as Uni talked about scalability. So we hope that this would be a more feasible idea.
Especially in a post-COVID world where the routing is dependent on the current situation of the whole environment.
Yeah.
So
Any more questions? All right. So any more questions, or are we done?
I don't have any more questions. The only other comment I would make is if you want to look at something as well, just doing you could basically do for the routing problem, if you were having trouble with the RL, you could also try a graph-based problem with sort of weights on the degrees, the vertices. In my own experience, RL sometimes can be very unstable and difficult to train. That might not have been your case, in which case it's totally fine.
Yeah, we actually did quite a lot of testing with the RL algorithm, and the results are we tested it out on our systems and on IBM Watson also. And so as you can see here, it's the time that it took to train the entire thing. So it's 81 milliseconds it takes to train on over 10,000 epochs. And given that you provide a valid state space, it's bound to converge at the desired values. And another advantage is that this doesn't use any fancy neural networks or other heavy lifting things. This is plain NumPy, and this is the Q-learning algorithm that we implemented here. So that means that this can be even used on low-level hardware. So yeah.
Awesome. Thank you.
All right. Thank you to Navscape for their presentation. Let's go on to the final team, 36-hour fitness.
Hello, today we present to you 36 slide.
Hey, Julie, I think you cut out. Do you want to just...
Oh, okay. Oops.
Good.
And it says my internet connection is unstable. Okay. Hello, today we present to you 36-hour fitness, your AI-powered personal fitness trainer. Because of COVID and social distancing, people can no longer go to the gym or attend in-person workout classes like they used to. Have you ever felt this way when doing a workout from home alone? No longer do we have a trainer or a friend next to us in person, pointing out what we're doing wrong and which way we should actually be moving our arms or bending our knees. A lot of these workout videos that we now rely on are difficult to follow and actually do correctly. Take Chloe Ting's ab workouts here, for instance. Lots of people have difficulty replicating her moves, and doing the workouts incorrectly isn't as effective and can even possibly cause you to get hurt.
So that's why we built 36-hour fitness, because social distancing and a global pandemic shouldn't stop you from achieving your workout goals. So 36-hour fitness is just like being back at the gym. You get and having your own personal trainer. You get real-time coaching and feedback on your exercise, making sure that your form is right. That's really important because it allows you to improve your form, which helps you prevent injuries and get a more efficient exercise and workout experience. Furthermore, our website has a gamification model that allows you to exercise and compete with your friends, encouraging you to exercise and giving you the motivation you need.
And we've automated our entire product end to end to make it as easy as possible for the user to use. And so just to jump right in, here's a quick demo.
Fitness. To get started, welcome to 36-hour fitness. To get started, we can either create or join a room. In this case, we'll be joining the leg day room. During the exercise phase, as you can see in the top row, there's the fitness video itself, a live feed of the webcam, as well as some session information and a leaderboard. And in the bottom, we have some analytics about the user's performance, starting with their score over time, computed using pose estimation and dynamic time warping algorithms, as well as some suggestions on whether they should focus on elbow, neck, knee, or hip angle to improve their form. So the user's doing pretty well right now, but what happens when things go wrong? As you can see, even though the user is just a little bit off, his score doesn't tank, because the dynamic time warping algorithm understands this temporal difference and accounts for it. But when the user is doing something completely wrong, of course he has to work on everything. Finally, here's the system working on a different, faster computer with another student on an...
Yeah, so I'm just going to pause this right here for a couple seconds. You'll notice that right now, my elbows aren't matching the instructor's. Like while she has hers up, mine are still down. And you'll see in the bottom row that it's for elbow angle, it says, watch your elbow. But the other angles, it says that I'm still doing a pretty decent job. But in a few seconds, you'll see what happens when I put my arms in the right place.
Another video.
And now you can see that the elbow angle indicator has changed. So to make all of this work, we've used and combined quite a few different components to make up our tech stack. And you can see some of the tools that we've used in the bottom row right here. But the three main components of our product, the first is the pose detection system. The second is dynamic time warping. And finally, we have our workout scoring algorithm. But for the first step, we need to find a way to get the pose of both you and your virtual fitness instructor. And we do this by extracting 17 different joint positions on each person through what's called the PoseNet neural network algorithm, which was developed by TensorFlow.js.
Now, I think the next component is actually one of the coolest parts of this, and it's called dynamic time warping. And if you look at the top right, this GIF will tell it all, because what happens, due to latency or some other issues, you're just a smidge off from the ground truth, which is any video you can pull up on the internet. What if you're just a little bit off? Your score shouldn't completely tank. And if you think about this from a technical perspective, if you just take one snapshot at the same time step, you're not necessarily performing the same component in the move. And that's why we use dynamic time warping. This is an algorithm. It's a dynamic programming algorithm that can essentially map any pose at time t from the instructor to any pose, not necessarily at time t on the student. So that way we can make sure that the score is actually based on what moves you're doing and not if you're exactly doing it at the exact same time. So that's one of the cool parts of this application. Moving on, I think one of the most interesting kind of components of this was that for me as a developer, I got addicted to this system, and it's something that I would honestly really use. So a big part of that is the part where we talk about, let's just say, the social aspect, where you're able to compete with friends, you're able to get together, watch a single video, because sometimes it's difficult to stay motivated when you're just alone. But in this case, we have gamification, we have tips on how to improve your form, and etc.
There's also a lot of applications for this. It doesn't just go for workouts exclusively. It can be applied to things like dance classes for fun and things like physical therapy. The options that you can do with this are kind of widespread because it just uses a general algorithm that we have created in order to make sure that your form is right and matches someone with more experience and more talent. Yeah, and that's all. So 36-hour fitness allows you to get better exercise, be more efficient, and work out with your friends. Does anyone have any questions?
What was the name of the dynamic time warping tool that you used?
So this is just it's a fairly standard DP optimization algorithm, so we implemented it.
Cool.
And one question, I'm only semi-familiar with DTW. Do you have to provide, I think, sort of like a cost function or a cost matrix? Because if my memory serves me correctly, it's unsupervised, right? And it basically is sort of like an unsupervised, almost like clustering over a time dimension to try and map two signals together. So if I'm not wrong, can you just comment on what kind of assumptions you made or what kind of cost function you used?
Sure. So the cost function is just defined very simply as the Euclidean distance between the ground truth and the video. And so just to like bring this up, since I don't think we clarified that exactly, you can like select any video you want and then upload it, and then you can figure out how to match that video. So you're absolutely correct. We define the loss function as I just mentioned. And then there's also another component to this, like you don't want your dynamic time warping to be matching your moves that you did at the beginning all the way to the end. So we have to impose some kind of window constraint. And this is also, a window constraint. So this is a fairly well-studied problem. And so our proposal is to integrate this integrate this solution into a non-trivial problem. So yeah.
Super cool. And I guess just as a final question, can you comment on what you might think some of the limitations might be? For instance, like does pose estimation fail on certain people, certain body types? I guess what would be the biggest weakness that you could see?
Yeah, I can actually cover this. Brandon, if you can go 3 slides forward.
Forward, like down?
Forward, yes. Yeah, this one. So if you look at the algorithm refinement, one problem that we had with a lot of videos is that it's like they constantly change angles, right? But the problem is with OpenPose, which is a 2D model, we can't really figure out what directions people are facing. So in order to solve that and be able to use workout videos in which people are at like 45-degree angles or like portfolios or something like that, we can use multiple cameras, i.e. like 2 laptops or a laptop and a computer or something like that, in order to create a depth perception and like get a 3D model that could help solve for that. That's the biggest problem that I think we're facing, and it shouldn't be too hard to fix.
I'm a little confused. Did you say you used OpenPose and PoseNet?
Oh, sorry. We use PoseNet. OpenPose is just, I think it's the original research paper that it was built off of or something.
Correct. Yeah.
Yeah.
Awesome. Thank you.
Thank you. All right. Thank you.
I'd love to see the code for this.
It's all on GitHub, so you can check it out later.
All right. Thank you.
Okay, so thank you to all our teams for presenting. We're going to give our judges some time now to discuss, and we'll be back for the closing ceremony in a bit.
Yeah, so if we could have Sean or Savannah move our panel judges into a breakout room, that would be great. And then for the rest of our finalists, if you could turn off your video and mute yourselves, that would be really helpful as well.
So you guys are moving us into a breakout?
Yes, you should get an invite very shortly. Sean will do it, I think.
Yep, I'm right there.
Awesome.
All right, you should have gotten an invite.
Okay, so we're gonna wait a little bit while our judges get situated and for an audience to roll in, but then once we're ready, we're gonna start closing. So for those of you that are just joining in now, we're going to take another 2 or 3 minutes just to kind of let everybody settle in and join. And then we will get started with our closing ceremony. Alrighty, so I think we are ready to get started. Okay, cool. So hi, welcome back everybody. Hope you've enjoyed the past 36 hours of hacking. We were like totally completely blown away by your projects this year. And while we know it can be hard to stay engaged in a virtual setting, especially with remote class and external obligations, your passion and creativity inspired our team and reminded us of why we're so excited to organize this event every year.
That being said, with a shift to a virtual HackMIT this year, we know there's plenty of room for improvement. you complete our feedback form at go.hackmit.org/hackerfeedback, you'll be entered in a raffle to win some special prizes. We'll also be sending this form out after the event ends.
Before we get started, however, we know that the nation has suffered an incredible loss this weekend, and the HackMIT team would like to take this moment to honor Ruth Bader Ginsburg and the path she paved for gender equality, civil rights, and so much more throughout her lifetime. Please join us now in a minute of silence for RBG. Thank you.
As a rundown, we will be announcing winners of our sponsor challenges, raffles, mini prizes, tracks challenges, and of course, our grand prize winners. If you're a recipient for any of our prizes, keep an eye out for further communication from the HackMIT team on how to claim your prize. First up, we have Arrow Street announcing the winners of our first sponsor challenge.
Thank you. We wanted to congratulate Team Covis, Team 466, for winning the best panel visualization for Arrow Street. And thanks to everyone for submitting a challenge. It was great to review, but congratulations to Team Covis.
Awesome. Thank you so much. So next up, we have CMT to announce their challenge winner.
I'm excited to announce that the CMT Detecting Crashes with Smartphone Data Challenge, their winner is Safe Drive.
Thanks so much, Nadia. Next up, we'll have Nick from DRW to announce their winner.
I'm excited to announce the data visualization hack winner for DRW is 36 Hour Fitness.
Now announcing the winners of their challenges, let's welcome Facebook.
Hey, just wanted to take a second to thank all the teams that submitted our projects. There was a large amount of submissions, and this just speaks to the need for building community and bringing us closer together during this pandemic. The winning team created a platform, functional end-to-end, that takes today's context and current events into account by letting people come together and achieve common goals ranging from local issues to social change. So congratulations to MatchMe for winning the Facebook Community Building Challenge.
Congratulations, MatchMe. Next, we'll have IBM announcing their winners. Layla from our team will be announcing their challenge winners.
Yeah, I'm super excited to be announcing the winners to addressing the community response to the COVID-19 challenge. In first place being WebShelf, second place being Guide and Evacuate, and third place being QuizZoom. Congratulations. There's also a second challenge by IBM, which is the Green Compute Challenge. And this year, the winner of the Green Compute Challenge was actually a tie between two projects. First being Control-Alt-Delete CO2, and second, Green Machine.
Congratulations to everyone who won a challenge from IBM. Next, we have NASDAQ.
The winner of our NASDAQ Most Creative Use of NASDAQ Quandl Datasets is the team Night Night. Congrats. We also have another challenge from NASDAQ, which is the most creative solution that enables 2+ musicians in separate locations to virtually record a song in one take with virtually no audio or video delay/lag in the resulting video recording. The winner of this was Tesla Calls. Congrats.
Thank you, NASDAQ. Next, we have Goldman Sachs.
Hey everyone, I just want to briefly thank everyone who participated in our challenge, which was the best use of the Marquee API. We hope you found the API interesting and easy to leverage, and we loved hearing about your different projects and the ideas and pathways you considered. So the winner of our challenge is Covis, project number 466. And yeah, thanks HackMIT for hosting us.
It was our pleasure. Thank you so much. So that concludes the end of our sponsor challenge prize winners. So thank you so much to our sponsors for helping make HackMIT 2020 a reality. We really couldn't have put on such a successful event without you. And of course, a big congrats to all of our winners and our, of our sponsor challenges.
Before we get into announcing our final overall prizes, let's take a quick break to announce the results of our Explorer raffles, mini events, meme contest, and superb Sunday submissions. So here are the winners of the mini events, whether it was a prize from some of the competitions or the raffles.
Yeah, so we'll take some time, let you guys digest this slide. There's a lot of names on here.
Yeah, feel free to take a screenshot. And as always, keep an eye out for future communication on how to claim your prize. Okay, cool. And next we have our workshop raffles. So these are the winners of, the workshop raffles. So take another minute to try to screenshot or maybe record the names if you're a winner. Okay, next we have our fun prizes. So the winner of the beginner prize is faithful.ly, which is an app to connect people by religion. The winner of our social media meme contest was Eric Wang for his spicy Vim meme. The winner of our superb Sunday submission was Dub My Professor, as their project was a 10 out of 10 epic meme. We're super excited that you guys went to our events and want to say thank you to everyone who participated. We've gone ahead and chosen our winners of the raffles and mini events, which we showed in the previous slides. Jamie, are we ready for the tracks prizes? Okay.
Awesome. So now we are going to move on to our track prizes. So this weekend, we asked you all to help make the world a better place by hacking in our education, health tech, urban innovation, and communication and connectivity tracks. And you guys didn't disappoint. The winners from each of our tracks will be able to choose a prize from the following list in the next slide. Let's see. So it's either $125 per person, AirPods 2, Amazon Echo, Beats, Powered Beats 4, JBL Flip 5 waterproof portable speaker, and a Bose SoundLink color Bluetooth speaker 2.
In education, our winner was Spacetunes. Congrats.
In health tech, we are awarding this track prize to Eyesight. Big round of virtual applause.
For our urban innovation track, the prize goes to Navscape.
And last but not least, the winning team in communication and connectivity is Loci.
And now the moment you've all been waiting for, our grand prize announcements. Our third place winners will get to choose from this list of prizes. So now that you've seen the prize, we're ready to announce the winner. The winning team is Latent Space. Please give a virtual round of applause and let's hear their acceptance speech.
So actually, I think that some of our prize winners are not here today. So I don't think we'll be getting acceptance speeches from our third place prize winner.
Oh man, okay.
Oh man. All right, on to second place. So the second place prize is gonna come from this list. So it's gonna be $750 per person, a Sonos soundbar, an Apple Watch Series 6, or an iPad Pro. And our winning team is the virtual classroom. Congratulations, another big round of applause. And would the virtual classroom like to give their acceptance speech?
Hey guys, can you see
Hello.
us? Hello.
Yeah,
So
we see you.
we want to thank you guys so much for giving us this experience. That we're just high school students, right? We came in with no expectations at all, and honestly, it's just been an amazing experience. Thanks. I want to thank the organizers for organizing such a good event, and just thanks in general to everyone for participating and for such an amazing event. Thanks, guys.
Yeah, thanks, guys. Thank you so much.
Awesome.
Okay, and now our grand prize winners, they're going to receive $1,000 per person. So that's a total of $4,000. And our grand prize winning team is 36 Hour Fitness. So congratulations to 36 Hour Fitness.
To reiterate, if you want a prize, please keep an eye out for our communication from the HackMIT team regarding how to claim your prize. Depending on your challenge, we will put you in contact with either a member of our team or your sponsor who will send you your prize.
And once again, don't forget to fill out our feedback form. There is a prize associated with this as well. And thanks so much for hacking with us. And we hope to see you at HackMIT 2021.
Bye.
Thank you. Boys.
Bye-bye.